Some of the biggest threats to our health are the ones we can't even see. They're often colorless, odorless, and just hiding in plain sight, sometimes in the very water we rely on every single day.
And that poses a huge challenge, right? For scientists, for public health officials, for everyone. How in the world do you track and fight an enemy that's completely invisible? Well, it turns out the answer might just lie in a really brilliant piece of chemistry that acts like a tiny secret agent. And it all comes down to this simple, almost magical color change. On the last, you've got this solution that's a really distinct pink color. But then, as soon as it comes into contact with the toxic heavy metal mercury, poof, the color vanishes completely. It's a crystal clear visual alarm bell, and we're going to break down exactly how it works.
But first, let's get properly acquainted with our villain, mercury. Now, it is a naturally occurring element, but it's our own human activities that have really made it a widespread and dangerous pollutant.
And listen, this isn't some small, niche problem. To get a sense of just how big of a deal this is, look at this. When the World Health Organization puts something on its list of the top 10 environmental threats to human health, yeah, you know the stakes are incredibly high.
So what makes this stuff so bad? Well, it gets released from industrial processes, right? Things like burning coal. But once it gets into the water, bacteria can transform it into something even more toxic called methylmercury. And this is where it gets really scary. It bioaccumulates. That means a little fish absorbs a tiny bit, then a bigger fish eats that fish and absorbs more. And it just keeps concentrating all the way up the food chain, right onto our dinner plates. Exposure can seriously damage our nervous system, our immune system, you name it, and it can lead to devastating illnesses like the infamous Minamata disease.
Okay, so the danger is clear. But that brings us right back to our original problem. If it's so critical to find this poison, why is it so hard? Well, the answer really lies in the tools we have, or maybe the tools we don't have. Our current ways of detecting mercury are powerful, for sure, but they're just not practical for widespread, on-the-spot testing. They're expensive, they use these huge, bulky lab instruments, they're slow. You have to literally take a sample from a river, ship it to a lab, and then wait. What we desperately need is something that is the complete opposite of all that. Something low-cost, portable, simple, and fast.
And that right there is where our hero comes into the story. Researchers have developed a new chemical sensor that pretty much ticks all of those boxes. And here it is. Now, don't get bogged down by the complex diagram. All you really need to know is that this molecule, which the scientists call receptor 1, has the absolute perfect shape to hunt down and trap mercury. It's like a molecular lock that's been designed for one and only one chemical key. And these graphs, they show just how good it is at its job. On the left, you see a bunch of lines. Each one represents the sensor being exposed to a different metal you'd find in water, things like lead, cadmium, zinc. Notice how they're all just kind of hanging out at the bottom? Nothing's really happening. But then look at that one line that spikes way, way up. That's what happens when you add mercury, whose chemical symbol is Hg. The sensor just ignores everything else and zeroes in only on its target. That's what makes it so brilliant. It's a sharpshooter. So, okay, we know it works, but how does it work? Let's pull back the curtain and look at the actual chemistry behind that disappearing pink color. It's really cool. The first key concept you need to know is something called aggregation. When you put receptor 1 in water, the molecules don't just float around all by themselves. No, they like to huddle together, forming these large clusters or aggregates. Think of it like a crowd of people. And it's this specific clustering, this crowd, that interacts with light to produce that vibrant pink color. And we can actually prove this is happening. This graph comes from a technique that measures how big the tiny particles are in a liquid. See that blue peak labeled 1? That's our sensor molecules, all huddled together in their little crowds. The graph shows they're forming these pretty big clusters, around 535 nanometers in size. So we know for a fact those clusters are there, and they're what's making that pink color. Now for the second key concept, disaggregation. So what happens when our villain, mercury, enters the scene? Well, the mercury ions come in and interact with the individual sensor molecules. And this interaction is so strong that it actually breaks up those big clusters, causing the crowd to disperse. Let's go right back to our graph. Remember that big blue peak that showed the large clusters? Now look what happens when we add mercury. That's the red peak. See how it shifted way over to the left? The particle size has shrunk all the way down to just 168 nanometers. This is the smoking gun. This is the proof that mercury is the agent that's breaking our clusters apart. The crowd is gone.
So, here's the crucial takeaway. The color change isn't a reaction in the way we normally think about it. It's a physical change. The clusters create the color. Mercury breaks the clusters. The color disappears. It is a beautifully simple and direct way to send a signal.
This is fantastic science, absolutely. But what makes it a real game changer is how easily it can be applied out there in the real world. So let's see how this incredible chemistry moves from a high-tech lab right into your pocket.
You don't need $1 million spectrometer or some fancy lab. The process is unbelievably simple. Step 1, add your water sample to the sensor solution. Step 2, take a picture of it with just a regular smartphone. And step 3, you analyze the color intensity of the pixels in that photo to get a precise measurement. That's it.
And just how precise are we talking? Using a standard smartphone, researchers could detect mercury all the way down to 89.4 nanomolar. To put that into perspective, that is an incredibly tiny amount. It proves this method isn't just easy, it's also ridiculously sensitive and powerful.
So let's just do a quick recap of what we've learned. We've got a new sensor that uses a simple pink to colorless change to signal that mercury is present. It's a total sharpshooter, ignoring other metals to find its one and only target. We now know this cool effect is driven by mercury literally breaking apart molecular clusters. And maybe best of all, it's so effective, it basically turns a smartphone into a powerful scientific instrument. This whole thing leaves us with a really fascinating final thought. By designing molecules that cluster up and then break apart when a specific target shows up, we found a new way to make the invisible visible. Now that we can do this for mercury, what other hidden threats, what other invisible dangers could this brilliant approach help us find next?